All right. Okay, so today we're going to follow on with what we were talking about yesterday, or last lecture. Today we're going to talk about co-state estimation. Using collocation at LGR points. Now, if you recall, in the Redau method, or the LGR method, so in the LGR method, state is approximated as, we say x of tau is approximated by capital X of tau, which is equal to the sum from I equals 1 to n plus 1 of xi Li of tau, where where n is the number of LGR points and tau 1 through tau n. So tau 1 through tau n are the LGR points, and tau n plus 1 is equal to plus 1 is a non-collocated point. And we have the fact that these Lagrange polynomials, in this case Li of tau, is the product from j equals 1 to n plus 1, where j is not equal to I, tau minus tau j all divided by tau I minus tau j. And this goes I equals 1 up to n plus 1. So there are n plus 1 of these polynomials. Now, remember that when we do these approximations and then we're doing collocation, we're always collocating at the quadrature points. So that's the key, is that we're always collocating at quadrature points. The quadrature points in this case are these n LGR points. So what I need to do is I need to differentiate this state approximation, which is going to equal the sum from I equals 1 to n plus 1 of xi times Li dot of tau. And when we differentiate this, now we collocate the result at the n LGR point. So I take x dot of tau j and I set it equal to f of xj uj, and this is j equals 1 up to n. No, it's because there are only n LGR points. So when we do that, we get the following system, where these coefficients, Li dot of tau j, becomes xi times Li dot of tau j is equal to f of xj uj, right? This is what happens when you do this. Sum goes from 1 to n plus 1. And then these coefficients here become the differentiation matrix. So it gives you the sum from I equals 1 to n plus 1 of d ji xi equals f of xj and uj. And again, j goes from 1 up to n. Now, when we write this in matrix form, we get the following. We get d times x, 1 to n plus 1, is equal to f 1 to n. So the right-hand side always contains the dynamics, or the vector field of the dynamics evaluated at the collocation points. So of course we can rewrite this as a constraint of the following form: d times x 1 to n plus 1 is equal to 0. Okay? So that's what we get when we're done. Now, the NLP, actually the NLP for Redau is simpler than the NLP for Gauss, because it doesn't contain that quadrature equation. So what we wind up with is, we wind up with the LGR NLP is as follows. NLP for LGR method looks like this. It looks like minimize phi of x n plus 1 subject to f1 colon n minus d times x1 to n plus 1 is equal to 0. And we get the constraint that x1 minus x0 is equal to 0. Or alternatively, we could write it in the, being consistent with the way in which we write things. We write it as x0 minus x1 is equal to 0. And you can see it's a simpler NLP. So what we do now is we want to figure out how to do co-state estimation for this NLP. And remember, this comes from the optimal control problem where we have a Mayer cost phi of x of plus 1 subject to the dynamic constraints x dot equals f of x and u, and x at 0 equals x at negative 1 equals x0. So if I form the Lagrangian of the LGR NLP, I get the following. I get L, which is my Lagrangian, which I want to make sure I don't write this down incorrectly, so we'll go through it carefully, is equal to phi, which is the objective function, plus we get the inner product of now these multipliers again. This is the same thing we got when we did this for Gauss. So those are the terms involving the collocation equations. And then we get this other term, which is the inner product of this Lagrange multiplier I'm going to call mu with x0 minus x1. Now, you can see that it doesn't look that much different from Gauss, except for the fact that there's no quadrature equation, because we don't have to estimate the state at the final point via quadrature, because it's already included as a variable in the NLP. So if we list out the variables, what we see is that the variables in this NLP are x1 all the way up to xn plus 1, and u1 all the way up to un. Now, if we differentiate that Lagrangian with respect to each of the variables, this is what we wind up getting. We wind up getting this, is that for j equals 2 up to n, we get the following result. We get the sum of from I equals 1 to n. And you have to go through every single step in the math in order to be able to show this. But you get dij times lambda I is equal to lambda j times the gradient with respect to x of f of xj uj. And this is j equals 2 up to n. Now you'll see that because what you get here is when I differentiate with respect to any of the values of x all the way up to from 2 to n, only place that n plus 1 occurs is in this equation here and in that term over there. So when I differentiate with respect to from 2 to n, I don't take any derivatives with respect to phi, because phi is not a function of x2 to xn. It's only a function of xn plus 1. And then this term over here is only a function of x1. So I'm only getting the interior parts, which are just basically the derivatives of this constraint over here. And so that's what I've basically written in that expression there. Now for j equals 1, the situation is a little bit more complicated, because when j is equal to 1, I also get the derivative with this term over here. So what I get is I get almost the same thing. I get I equals 1 to n. I get d I1 times lambda I is equal to lambda 1 times the gradient with respect to x of f of x1 u1. That part is the same as what I got before. You'll see it looks exactly the same. But there's another term there, which is mu, right? Because if I take the derivative here with respect to x1, I get negative mu, right? Because there's a x0 minus x1, so I get negative mu. And this is for I equals 1. Now, the next thing I need to do is I need to take the derivatives with respect to u. So if I take the derivatives with respect to u, you'll see that the only place that the u's occur is over here. So what I'm going to get is the following result. I get the gradient with respect to u of, I get lambda j times the gradient with respect to u, f of xj uj equals 0. And this is for j equals 1 up to n, right? Because there are n values of u. And then the last thing is, if I differentiate with respect to xn plus 1, what I get is I get the gradient with respect to x of phi, which is a function of xn plus 1, and that has to equal, if I take this to the ascending, the whole thing equal to 0. So if that has to equal dn plus 1 transpose times lambda 1 to n. All right? Which you can also write this as the sum, as a summation, which it looks like this. It's the summation from I equals 1 up to n, because I'm taking the transpose of the last column of d, right? And I get d n plus 1 comma I times lambda I. So there's nothing different about what I've written here. It's just taking the I comma n plus 1, the last column, right? I take the elements in the last column and I multiply them across. I get that. Now what we need to do is we need to transform this system of equations to a system that looks like the first order optimality conditions of the optimal control problem. So if you remember, the first order optimality conditions of the optimal control problem, so if I write down from the calculus of variations, we would get the following thing. We would get that lambda of plus 1 is equal to the gradient with respect to x of phi of x n plus 1. We'd also get lambda at minus 1 is equal to mu. And we'd get lambda dot of tau is equal to minus the gradient with respect to x. Let's make sure that I write this the same way in both cases. You get the minus the gradient with respect to x, little x, of the inner product of lambda of tau with f of x of tau and u of tau, right? So that's what we would get if we were going to apply the calculus of variations. So what we want to do is we want to make these equations over here look like those equations over there. So the way we do this is as follows. Is suppose we define a new differentiation matrix, and I'm going to call this differentiation matrix d dagger again. But in this case, unlike Gauss, this is actually an element of Rn n by n, where it looks like this. D dagger 1, 1 is equal to minus d11 minus 1 over w1, and dij dagger is equal to minus wj over wi times dji, right? And so this is everything except that one. Now, if I define that matrix, and I'm also going to define the following. Also, I'm going to let the following be true. Lambda 1 to n is equal to W inverse of big lambda 1 to n, and lambda n plus 1 is equal to d n plus 1 transpose times lambda 1 to n. These right here are the estimates of the costate at the n, L, G, R points. And this is an estimate of the costate at tau equals plus 1. Now, if we do that, and we use these equations that we have over here, this is going to get a little bit difficult, but because I have to erase these because I don't have enough board space to do this. But if I transform each of these equations sequentially, what I wind up getting is as follows. Is I get, for the equation involving the endpoint, what happened? What's that? Oh, it's in the way. I'm sorry. Okay. Okay. Thank you. So if I do this, then in terms of d dagger, we have, so the first one just becomes lambda n plus 1 is equal to gradient with respect to x of phi of x n plus 1. Now that comes out simply because we've defined the final value of the costate to be d, this is not a dagger, this is a transpose, to be the transpose of the last column of the D matrix with these multipliers. And if you remember, if we look back, we see that if you look back at the condition that we got from earlier, which I just erased, we got that the gradient with respect to x of phi of x n plus 1 was equal to d n plus 1 transpose times lambda 1 colon n. So given the way that we've defined little lambda n plus 1, which is the costate estimate at the final point, it's equal to dn plus 1 transpose times these multipliers. It turns out that this is the same, right? Because if I set little lambda n plus 1 equal to big lambda n plus 1, big lambda n plus 1 is an estimate of the costate, sorry, little lambda n plus 1 is an estimate of the costate at the final point. It's equal to dn plus 1 transpose times lambda n plus 1, but that is just equal to the gradient, and that's what I already know, so this equation doesn't change when I put it into the transform system. So in the transform system, it looks exactly the same. So the next equation, which involves the d-dagger matrix, is that the sum from I equals 1 up to n of, sorry, j equals 1 to n, of dij dagger times lambda j is equal to minus lambda sub I times gradient with respect to x of f of x I ui. Okay? Okay? This is for I equals 2 up to n. So you see that in this particular case we get a transformation that looks like that. And then lastly, we get the following transformation, which is that lambda I times the gradient with respect to u of f of xi ui has to equal 0. And this is for I equals 1 up to n. Now, you can see that the way in which this now can be broken down is as follows, is that we know that D is a differentiation matrix for the space of polynomials of degree at most n. So this means that if I apply D to 1, I should get 0. But what that tells me is, it tells me that d1 through n times 1 plus dn plus 1 has to equal 0, which tells me that dn plus 1 has to equal minus d1 through n times 1, which another way of writing that is that it's basically a linear combination of the columns, of the first n columns of the matrix D. So I multiply by 1, just multiplying by a column vector of 1s. What I get is that d n plus 1 has to equal minus the sum from I equals 1 to n of d I. Okay? That's all that tells me. So now, given that, I can make the following substitutions, which is that I know that lambda n plus 1 has to equal what I've got there, which is d n plus 1 transpose times lambda 1 through n. That is equal to the sum from I equals 1 to n of di n plus 1 times lambda I, right? But that, in turn, if you look at this, you'll see that that is just equal to minus the sum from I equals 1 up to n, and then the sum from j equals 1 up to n of lambda I d ij. So I haven't done anything there. All I've done is I've just done a direct substitution. And that, if I write this in terms of d dagger, is equal to lambda 1 over w1 plus the sum, and this is from I equals 1 up to n, and j equals 1 up to n, of lambda j times d ij dagger times wi over wj, which is equal to lambda I all divided by w1 plus, sorry, this is lambda 1, plus the sum, and again I'm going from I equals 1 to n, and j equals 1 to n. But now what I'm going to do is I'm going to write this in terms of the matrix that I get when I do the full substitution, right? So I get this result. I get this result right here, because what I've done is I've substituted in for lambda j, and I've written it in terms of lambda I, which in turn is equal to the following. So this is equal to mu minus the sum from I equals 1 to n of wi times lambda I times the gradient with respect to x of f of xi and ui. So now if you look at this, what this says is, this over here, remember, is lambda n plus 1. So this says that the costate at the endpoint that I'm missing one endpoint, right? I don't have the costate at the final point because it's not a collocation point. But I can get the costate at the final point from this relationship right here. And you remember that from the earlier result, we had that mu, if I recall the earlier result, you have that we have this term in here. Now, if you look at the result that, so look at this result, that the sum from j equals 1 to n of d1j dagger times lambda j equals minus lambda 1 times the gradient with respect to x of f of x1 u1 minus or plus 1 over w1 times mu minus lambda 1. Now, this right here, if this term didn't exist over here, this would look a lot like this over here. It would look like lambda dot is equal to minus the gradient with respect to x of the inner product of lambda with f, right? If this were 0. So I could write it this way. Say if mu were equal to lambda 1, then we would get something that looks approximately like that, right? Because what I'd have here is this is an approximation to the derivative of lambda, which is an approximation to lambda dot at tau equals, at the first point, for I equals 1, so at tau equals minus 1. And this is dh dx. So if this term were equal to this, if this whole thing would go to 0, then what I could do is I could say, well, lambda 1 is equal to mu, so then this over here could be substituted, and I would get lambda n plus 1 is equal to lambda 1 minus this thing. But this thing right here is an approximation to the integral of the costate dynamics, right? So let's go back down here. I say, suppose lambda 1 were equal to mu, okay? We don't know that right now, but let's suppose that were true. Then what we'd be able to write is lambda n plus 1 is equal to lambda 1, and I'm going to write it this way, plus the sum from I equals 1 to n of minus W, oh, so I'm going to write it this way, Wi times minus lambda I times the gradient with respect to x of f of xi and ui. Okay. Now look at that. This right here is minus dh dx, right? So this is like, and this is the quadrature weight, right? So given the fact that this is the quadrature weight, what this is saying is that this is a quadrature approximation to the integral if this is true, right? Only if this is true. Well, it turns out that in the Redal method, one of the things that we get is that it's not exactly true that lambda 1 is equal to mu, but one of the properties that we find is that as n gets larger, so as n increases, it turns out that we get the following result, which is that lambda 1, or I should say mu, approaches lambda 1. So in other words, so alternatively, mu minus lambda 1 becomes approximately 0. So that's just a function of the fact that we are doing implicit integration when we use the Redal method. So in the end, our costate estimate can be developed as follows. So the costate estimate for LGR, which actually you can see is a little simpler than the one for Gauss, which is that lambda 1 colon n is equal to W inverse times lambda 1 colon n. And we get lambda n plus 1 is equal to d n plus 1 transpose times lambda 1 colon n. And we get lambda at lambda 1 is approximately mu. So we can get a full slate of information to do the costate estimate. So that's now it turns out that lambda 1's not approximately mu because it actually, you can see up here that we're estimating this. So this right here is only used to compute lambda n plus 1. But we can also get lambda n plus 1 from this equation. So basically what it comes down to is when we're all done, we can ignore this equation, and we can ignore all this other stuff, and our costate estimate looks as follows. We get a complete costate estimate simply by doing the following. So the final costate estimate looks like this. Is lambda 1 through n is equal to W inverse capital lambda 1 through n, and lambda n plus 1 is equal to d n plus 1 transpose times lambda 1 to n. So this first is the costate estimate at tau 1 to tau n, which are the n LGR points. And remember that tau 1 is equal to negative 1. And this is the costate estimate at tau equals plus 1. And that's it. That's the final result. And you can see it's a simpler result from the one you get from Gauss, because the one you get from Gauss, you have to deal with the final and the initial costate separately, whereas with Redal, you only need to deal with one endpoint. And it's done very easily by just computing it using the last column of the differentiation matrix. So that's pretty much it for Redal. I don't have enough time in this lecture to go over Lobato because it's going to take more than 10, 15 minutes or whatever I've got here. So I'm going to stop, and we'll pick this up next lecture with Lobato.